Hi everyone, my name is Prashanti Anderson and today I'll be telling you about some recent work on private algorithms for linear regression. This is joint work with my amazing co-authors, Bakshi, Majid, and Tiegel. In this problem, we have a bunch of data points which may be high dimensional and we want to understand linear relationships between the variables in the data. This has a ton of applications from econometrics, drug design, quantitative social sciences, and more. And in these applications, we should think of each of these individual data points as being the information of a single person. For example, in the application of drug design, they might be the medical records of one individual. And in these applications, we want to compute some linear fit and release this linear fit to the world without revealing information about individual data points to the extent possible. There are simple algorithms which work quite well for this problem if we don't care about privacy. For example, ordinary least squares is like a very simple algorithm that you learn in STOC 101. However, this can leak information about individual data points. If we change this blue point over here to the red point up here, the OLS fit changes noticeably, and thus we can learn whether we have the red or the blue point in the dataset by looking at the output of the algorithm. In fact, there are concrete and efficient privacy attacks on many common algorithms for linear regression, which are able to do things like, for example, determine whether a given data point was part of the input dataset. Given this state of affairs, it's an important task to try to design algorithms for linear regression which do preserve privacy of individuals to the extent possible. And perhaps the gold standard for designing private algorithms are algorithms which satisfy differential privacy. Informally, differential privacy says that the output doesn't change too much if you change a single data point. And in addition to formalizing what it means for an algorithm to be private, it also quantifies the amount of privacy loss. One natural question is what the price of privacy is. And in fact, there is a fundamental trade-off between privacy and accuracy. For example, in the application of the US Census, they found that they had the following trade-off between accuracy and privacy loss. This trade-off is in fact fundamental. A result by Dinara and Nissim in 2003 showed that sufficiently accurate statistics cannot be private, so you can't have your cake and eat it too. However, even if we can't be 100% private and 100% accurate at the same time, designing better algorithms can help to improve the trade-off that we get between privacy and accuracy. This leads us to the main question of this talk. What is the optimal accuracy-privacy trade-off for computationally efficient estimators for the problem of linear regression? Our main result is that we give a polynomial time estimator achieving the optimal accuracy-privacy trade-offs for linear regression among computationally efficient estimators. Formally, the model we consider is that of Gaussian linear regression. We have a bunch of IID samples where xi is drawn from some high-dimensional Gaussian with unknown covariance structure, and yi is generated by taking the inner product with some unknown parameter vector theta and adding a little bit more Gaussian noise. And given IID samples from this model, our goal is to get an estimate of theta which achieves low generalization error. Specifically, low generalization error means that if I'm given a new sample x from the model and I try to predict y, I don't do too much worse than what I would have done if I had known the true parameter vector theta. This turns out to be equivalent to parameter recovery in the following sigma 1 half norm. So for the rest of this talk, I'll just focus on getting parameter recovery in the following norm. And note that if I only have access to an estimate theta hat and the true parameter theta, I can't even evaluate this norm. So in order to know whether an estimate is good, I need to have some estimate of the covariance sigma, and this will turn out to be important later on. Formally, the notion of privacy that we consider is that of differential privacy. A mechanism is pure differentially private if for every pair of input datasets x and x prime, which have Hamming distance 1, or which differ on a single point or a single individual, we have that the output doesn't change too much under x versus x prime. And specifically, for every subset S of the outputs, the probability that the mechanism outputs something in S is within an e to the epsilon factor when I run the mechanism on x versus on x prime. And so if epsilon is very small, we can think of this as being within a 1 plus epsilon factor. And I want to emphasize that even though the model we consider is random, the notion of privacy is a worst case notion. So we will require that our algorithm or our mechanism is always private even if we give it some data set that is not from the model. Prior to our work, there were several different algorithms which achieved private guarantees, but most of them achieved a slightly different notion of privacy called approximate differential privacy. Approximate differential privacy is a weaker notion of privacy that works under fewer assumptions, but it cannot achieve pure differential privacy unless you think of the second privacy parameter delta as being exponentially small. Prior to our work, there was only one algorithm which achieved pure differentially private guarantees, which is the work of Ozzy, Ullman, and Zakhanov in 2023. It was not an efficient estimator, it ran an exponential time, and it achieved the following sample complexity, which I'll return to in a bit when I compare it to our algorithm sample complexity. Our main result gives a pure DP algorithm for this problem. It works under the assumption that the covariance and the parameter vector theta are bounded. This is in fact a necessary assumption for private algorithms, and it's quite a common one in the pure DP setting. The algorithm runs in polynomial time and with high probability outputs an estimate theta hat, satisfying the desired generalization error guarantee. And finally, the sample complexity required scales as d squared over alpha squared plus d over alpha epsilon plus d log r square root L over epsilon. Here, we could think of the first term as the price of efficiency and the second two terms as the price of privacy. Specifically, there is an information theoretic lower bound that says that you cannot get a better dependence on the privacy parameter epsilon than the second two terms. Furthermore, a combination of prior work from Georgiev and Hopkins in 2022 and Diak-Nicholas, Kong, and Stewart in 19 show that if you have this optimal dependence on the privacy parameter epsilon, you must pay d squared over alpha squared if you have a computationally efficient estimators. Specifically, the first prior work shows that private algorithms must be robust, and the second shows a computational lower bound against robust algorithms for linear regression. The main prior work which gave a pure DP algorithm was that of Ozzy, Ullman, and Zakhanov in 2023. Their work gave an exponential time algorithm which achieved a sample complexity which scaled as d over alpha squared plus d log r plus kappa over alpha epsilon. Compared to their work, we have removed the dependence on the covariance is condition number kappa, and we are also able to get a dependence which scales as d log r over epsilon rather than d log r over alpha epsilon. However, we do incur a dependence of d squared over alpha squared compared to their d over alpha squared. This is because we run into computational bottlenecks, whereas their algorithm runs in exponential time, so it's not subject to the same SQ lower bound that our work is. Our techniques have several other applications. We are also able to give efficient approximate differentially private algorithms for regression, as well as efficient DP algorithms in both the pure and approx DP setting for covariance-aware Gaussian mean estimation, or the problem of estimating the mean of a Gaussian where the covariance is non-identity and unknown. Now I want to tell you a little bit about some of the techniques that go into our pure differentially private algorithm. Our algorithm uses the exponential mechanism, which was introduced by McSherry and Talwar in 2007. The high-level idea is to sample a parameter vector theta tilde from the following distribution, where the probability of every point is proportional to x of negative epsilon times some score function, which is a function of the dataset x and theta tilde. Here, we should think of points which are low scoring as being good outputs or good estimates because they will be outputted with higher probability. Furthermore, if the score function is a low sensitivity function, then McSherry and Talwar showed that sampling from this distribution does in fact give you a pure DP mechanism. And specifically by low sensitivity, I mean that if I change the dataset x by 1 point, then the score of every parameter theta tilde changes by at most 1. And furthermore, if the score function gives low score to enough accurate points, then if I sample from this mechanism, I'll get something which is low scoring and thus a good estimate with some good probability. Designing score function is a bit of an art. To design a score function is to design a PRDP estimator. And in recent years, it turns out that a good choice of score function is the answer to the following question. How many data points do I have to change such that a robust regression estimator outputs an estimate which is close to theta tilde? Similar choices of score function have been used in several prior works, and this score function is also sometimes called the inverse sensitivity mechanism. Note here that the choice of a robust regression estimator is what makes this mechanism accurate. If I only changed a few points, then a robust regression estimator should still output an estimate which is close to the true parameter theta. There's been a long line of work which shows how to design robust estimators. You can see Diaknolis and Kane's work for a survey. And designing new robust regression estimators, which play nicely with this transformation, is part of our work. However, it's not a part that I'm going to focus on in this talk today. Instead, I want to focus on what makes this question a low sensitivity function. Note that if I have a notion of closeness which only depends on the estimate and theta tilde, say something like L2 closeness, then if I change 10 data points to make a robust regression estimator output an estimate which is close to theta tilde on x, if I have a data set which is close to x and only differs on 1 point, then I can just change 11 data points, the points that I originally changed plus the data point that differs, to get the robust regression estimator to output the same estimate, which is still close to theta tilde. However, in our setting, the correct notion of closeness isn't quite this simple. In order for this to be accurate, we want theta tilde to be approximately as good of an estimate for the true parameter as the output of the robust regression estimator. However, in our setting, this is not governed by L2 closeness, but instead by this sigma 1/2 norm. Formally, we can say that the score of any point theta tilde is the minimum eta such that I can change eta points and get the robust regression estimator theta hat of x prime to be close to theta tilde, where closeness is closeness in the following relevant sigma 1/2 norm. There are several challenges in implementing this in our setting, and the first and most fundamental is that as written, the score function is not a function of x and theta tilde. It also depends on the unknown covariance sigma, which is unknown. The score should be a function of only things that the algorithm knows because the algorithm is going to need to compute it to sample from the distribution. The second challenge is that so far I've just told you an information theoretic argument of how to get a PRDP estimator. However, in the end, we're able to give an efficient estimator. So it turns out that a recent line of work gives a way to make these types of estimators efficient using connections to the sum of squares hierarchy and convex relaxations. And our work will also be able to do the same using a small twist on the prior work of Hopkins, Kameth, Majid, and Narayanan. We do face some unique challenges due to our setting, but I'm not going to focus on those today. Instead, I want to tell you a little bit about how we make the score function only a function of x and theta tilde. And before I tell you what we do to resolve this question, I first want to tell you a couple of approaches which don't work. One natural approach is to try to throw away the geometry induced by the covariance and instead enforce an L2 constraint. Here, we still need that the estimate and theta tilde have similar generalization error. So they'll need to be closer than alpha and L2 norm. In fact, they'll need to be alpha over lambda max close. So it turns out if you follow the argument all the way through, you'll require d log kappa over alpha epsilon many samples to output an accurate estimate, where kappa is the condition number of the covariance. And this is larger than the d over alpha epsilon many samples that we were shooting for. Intuitively, the reason why this happens is that you're being too wasteful in throwing away the geometry. There are points which should have been low score, but they would satisfy the above constraint with sigma 1/2 and not the L2 constraint below. And because there are fewer low scoring points, you need more samples to output a low scoring and thus accurate estimate. So we just saw that you actually do need to capture the true geometry of a space induced by the covariance. One natural substitute for the covariance is the empirical covariance of the samples X. However, this is going to be too high of sensitivity. The empirical covariance actually has quite high sensitivity because by changing a single point, I can drastically change the covariance in a single direction. And thus, the score of points might change very dramatically. If you instead try to replace sigma 1/2 with a private estimate of sigma to preserve sensitivity, this will take d squared over alpha epsilon many samples, since sigma is a d squared dimensional object, and privately estimating it will incur this cost. And so we want to avoid the cost of privately estimating sigma. So here we've seen that we do need to try to capture the geometry, yet functions of x are either too high of sensitivity or too expensive to compute. The natural remaining option is to try to use a function of x prime. And this is actually quite close to what will work in the end. One natural function of x prime is sigma prime. And if I replace sigma 1/2 with sigma prime 1/2, then this does in fact preserve sensitivity. However, we do also need to make sure that it preserves accuracy. This is accurate if we have that for low scoring points, sigma prime is actually quite close to the true covariance sigma. However, this is not the case as written. By changing a single point, I could make the covariance sigma prime very far from the true covariance sigma. However, this does turn out to be true if I instead also require that x prime is nice in the following way. It is outlier free or that its moments are well behaved. The condition that we use is quite common in the robust stats literature and is called 4:2 hypercontractivity. This outlier free condition is sufficient to show that for low scoring points, sigma prime is quite close to the true covariance sigma, and thus we have that low scoring points are in fact good estimates for the parameter theta. So far, I've just told you how to get an inefficient estimator, but as I mentioned before, you can relax this score function using the sum of squares convex hierarchy to make all of this that I've told you about efficient. To wrap it up, I want to leave you all with some takeaways about how our work extends prior work. Prior work gave an efficient exponential mechanism for statistics problems with instance-independent error measures, for example, closeness and L2 norm. Our work extends prior work to give an efficient exponential mechanism for problems with instance-dependent error measures, for example, parameter recovery in the sigma 1/2 norm. We are able to apply our ideas and techniques to two problems, Gaussian linear regression and Gaussian mean estimation, where the covariance is unknown and non-identity. Finally, I want to mention some open questions. The first is whether the sample complexity for private linear regression can be improved in the approximate DP setting. In the pure DP setting, we know that our sample complexity is optimal. However, in the approximate differentially private setting, the situation is a bit more nuanced. And it's possible that you can get a better sample complexity dependence on D than our algorithm, which still pays the D squared over alpha squared in the approximate setting, by incurring a worse privacy dependence or a worse dependence on the privacy parameter delta in the approx DP setting. The second open question that I want to mention is whether there's other applications of this efficient robustness to privacy transformation. And one problem in this area where there's a gap between efficient and inefficient private estimators is that of density estimation for Gaussian mixture models. Thank you for listening, and you can find the full version of our paper at the link here or scan the QR code.